Hello everyone, do let me know if I am clearly visible and audible to all of you. Welcome to Vedantu NEET English everybody. Do let me know if I am clearly visible and audible to all of you or not. Yes students, yes everybody. Hi Krishna, Guru, Sarav, Dora, Rachuri, Lanchin, thank you. Okay. Awesome, awesome, awesome. Ma'am, start the session. Yes, we have started the session. And I'm going to teach you as it is from your NCERT PDF, right? That you can see over here, right? As it is, we'll see every single thing here, every single line I'll tell you, right? It's like if you study NCERT line by line from me, right? After this, you don't need to. You just have to revise it once before your exam. And please have your NCERT as well, right? I'm from DNA batch. Awesome, awesome, awesome. Welcome, DNians. Yes, awesome. So, everybody, ma'am, is this is more than enough. Trust me, if you're doing NCERT, DNF block from NCERT, it is more than enough. You don't need to do any other, no other book you need, no other book guys you need, right? Even my lectures you don't need to watch, right? My notes you don't need to see, right? If you're doing NCERT, nothing you need to do, right? That's as simple as that. Everything will be there from NCERT only, so you don't have to worry about anything, right? Okay, so let's start the session. And guys, these NCERT line by line sessions are going to be in this setup, because you know, here I can zoom in, here I can zoom out the statements. And if you remember, when we did it previously in the last session, we faced a lot of problems because I was teaching you NCERT line by line on the smart board, and students were like, ma'am, brightness is too much. There is no concern about brightness over here. This will be as it is, like that I am saying, you are saying as it is. There is no concern about brightness. First thing, I can zoom it in, zoom it out, right? Your notes will be directly prepared from this PDF itself. So you can, I'll also give you the PDF in the description box, right? You will get the PDF, everything you will get, guys, right? All you have to do is you should have your NCERT side by side, right? We need Shreyas sir and entire old team. Don't worry, it will be there. It will be there, right? Firstly, we also want to see your efforts. If you're like, yes, you guys are also putting the efforts, right? Team will surely join, right? Team will surely join. Don't worry about that. We are always, we have not left you, right? Okay, don't worry about that. Yes, everybody? Okay. So, for our English team, everybody, for Baswa sir, for Gopika ma'am, for Shreyas sir, for Diksha ma'am, just write down green hearts and fire emojis in the chat box. Everybody here. Let's start the session. I'm super excited to teach you DNF block from NCERT line by line. Let's start. Yes, everybody, let's start from here, right? As I mentioned, I'll teach you every single line from here. Now, if you talk about DNF block, right, iron, copper, silver, gold are among the transition elements that have important roles in development of human civilization. We know silver prices are going up and down, up and down. Gold prices are like shooting high, right? So they are all very important in our daily life, right? So if you talk about copper wires, iron is used in our daily life so much, so it is very important for human civilization. And all these metals that we are writing here, they actually belong to D block. They actually belong to D block, right? Then the inner transition elements such as this is THPA, that we will talk about, right? What are these elements? Are proving excellent sources of nuclear energy in modern times. Actually, now these elements are actinoids, and actinoids is a part of F block, right? That's why we'll study it later on. The major part of this particular chapter is D block, right? That we are going to talk about. So let's firstly, today though we are not going to move towards F block, so there is no point of telling you about lanthanoids and actinoids. So we'll only talk about D block in today's class, right? So we are saying that the D block, guys, everything is clearly visible now. Will you complete this chapter today? See, completing this chapter today in detail is impossible, right? Okay, if I say that, guys, I will not even miss a single line, right? You all know that last year I have taken around 9-hour lecture from NCERT line by line from this one, right? So it's impossible to do it in 4 hours. It is possible, but for that I'll have to skip so many things that I don't want. If you're having trust on me, if you're showing faith in me that, ma'am, if you're teaching this NCERT line by line to us, I don't have to read it myself, right? That means you're showing that trust on me. Then how can I break your trust, right? So I don't know, it will be completed maybe by tomorrow. Maybe I'll need 3 parts of it, but I'll try to complete it by tomorrow, right? Okay, so the D block of periodic table contains elements, groups up to group number 3 to group number 12. Now I'll just show you the periodic table. Let me see. Wait a minute. That a periodic table is not there mentioned in NCERT. No worries, no worries. So what we'll do, I'll just show you this here. I'll just make a rough diagram here. How does periodic table look like? This is S block, right? If you see here, you will have D block and here you will have P block, right? Here you will have P block and here you will have helium, right? That is going to be a full on summation, right? Okay. Now if you see it from here, this particular is S, this is D, this is P. Then, ma'am, where is F block? F block is actually over here. Okay, firstly we need to visualize that what exactly is there. Now this is group number 1, group number 2, and 3, 4, 5 up to 12 groups are over here in D block, right? And then in P you will have 13 to 18. Now this section, that is P block, we will have a different chapter that is dedicated to P block, in which we are going to study 13 to 18. Each group we are going to study in detail, right? And this section, that is D block and F block that I am mentioning here, this D block and this F block, that we are going to study over here, right? Okay, that we are going to study over here. Now for that you must remember that S block is not in your syllabus, but little bit will have to study, and that we have already done in periodic classification. If you want me to take NCERT line by line of that as well, I'll take it in the end, or I'll take it before P block, right? Okay. Now let's see this, right? This is S block. Now what you will see in this D block, what exactly is there? Let's erase, let's focus on this one. In this D block, what you exactly have? In D block, guys, here you have like around 3 to 12 means there are 10 groups in the D block. 10 groups you have in D block, right? Okay. That starts from which series? We'll talk about that. There are 10 groups. Till now, just remember that there are 10 groups in the D block, right? From 3 to 12, right? Okay. So let's talk about this here. Now they are saying from 3 to 12 you have 10 groups here, in which D orbitals are progressively filled in each of the 4 long periods. Now they are talking about periods here. Let's again move to this one. Ma'am, what periods, ma'am, they are talking about? Let's talk about that, right? Now we are saying, if you say how many periods it has, then it has 4 periods in the D block. Ma'am, what do you mean by 4 periods over here? Let's talk about that, how it has 4 periods. So in the section of, wait a minute, periods here, what we have, first period will be this one, second period, third period, 1, 2, 3, and that will be your 4 periods. So I'll draw it like this, 1, 2, 3, and this is 4. So what we are saying here, that you have, arey yaar, why this is getting erased? Chalo, I'll just draw it again. Okay, 1, 2, 3, 4. 4 periods and 10 groups are there in your D block, that you should remember, right? Now if I talk about what is the name of these periods, let's talk about that. Now I'll just erase this one, right? All of this you should erase here, because that is of no use to us. As of now, that is of no use to us, right? So we are focusing only on D block, so I'll only focus on D block here. If you see 4 periods, they have different names, right? So what is the name? The first period, that is called as 3D series, second is called as 4D, third is called as 5D, and first period of D block, I am saying, is called as 3D, then 4D, then 5D, then 6D, you know. And we know that in a periodic table, actually how many periods are there? There are 7 periods here. That means if you talk about S block here, it has 1, 2, 3, 4, 5, 6, 7 periods here. That means in total, out of those 7 periods, D block is only using 4 periods here. That means the 3D series is actually a part of which period? 3D series is actually nothing but it is 4th period, right? 3D series is nothing but actually it is 4th period. What is 4D series, guys? 4D series is actually 5th period, right? 5D series is actually 6th period. This is very important, small points that students totally get confused in. Ma'am, 6th period 6D series. No, 6th period is 5D series, right? Okay. Then you have, this is 6D series have 7th period, right? Okay. That is about the D block periods. 4 periods you have, 4th, 5th, 6th and 7th period. First 3 periods do not have any filling of d orbitals. Okay. Yes, guys. First 3 periods. Here you will have 1, 2, 3 periods, and it starts from the 4th period. This is first, second, third, 4th, 5th, 6th, 7th. First 3 periods do not have any filling of d orbitals, right? Okay. Then see one more thing here. That this 4th period is actually called as first, second, because these metals are called as transition metals. So this is also called as first, second, third, fourth transition series. So it has different names, right? Okay, it has different names. According to that, we will see, right? Okay, I hope so this thing is clear to all of you. You will get the PDF of whatever I write here as it is, you will get in the description box, right? Okay, so now things will be more easy for you to understand. Now we are saying F block consists of elements. Now F block is what? Elements in which 4f and 5f orbitals are progressively. Ma'am, what is F block? Let's see that over here in the periodic table. Now if you see in the this 5D series, right? In this 5D series over here, right? What you will have is, you will have the filling of 4f orbitals as well, and here you will have the filling of 5f orbital as well. So what exactly happens here? In 5D series, in group number 3, there is an element that we have over here. In 5D series, there is an element that we have here, that is lanthanum, and here there is an element that is actinium, right? So lanthanum and actinium belongs to group number 3, right? Okay, in group number 3, if I wait a minute, if I make it like this, what I'll do, I'll just add a new page here. Wait a minute. I'll just add a blank page here. right? So that you can understand things even more clearly, right? Because this base, if the base is clear, then things are going to get clear. If the base is not clear in your head, then you're going to get confused only, right? This is S block, right? If I want to draw it little, okay, this is S block, right? And here from the fourth period you will have D block, and here you will have P block. That P block and all we are not going to talk about. Our focus is not that, right? Our focus is understanding D and F block, that what is the placement actually, right? So I'll just ignore D and F block here. You don't have to worry about that. I'll just draw few groups here. This is 3, this is 4, this is 5, this is 6, 7, 8, 9 and 10. Okay, now let us make little more difference. 1, 2, 3, 4, 5, 6, 7. Arey yaar, what is happening? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, these are the groups, and here they are divided into 4 periods. 1, 2, 3, 4. Okay, this is about the D block. I'm only talking about D block here, a random thing I am drawing. So why I'm drawing this thing here, so that you can understand. You can also visualize, okay, ma'am is drawing, ma'am. If ma'am can draw, I can also draw, right? So guys, this was your 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th and 12th. That is the group, right? Now to understand lanthanoids and actinoids, you must know that here you have lanthanum, right? Here you have lanthanum, right? Yes, here you have lanthanum, and here you have actinium, right? Okay, and here after lanthanum you will see a weird gap here. After lanthanum, what you will see, the next element, right? Here the number, lanthanum number is, what is the atomic number of lanthanum? Lanthanum is 57, and after this the next will be 72, right? Okay, so where are the other elements? Where are the rest of the elements? So actually the rest of the elements, the gap that I have put across here is actually your F block, right? So after lanthanum, whatever you have is actually here in 4F series, right? And whatever you have after actinium is actually there in 5F series, right? That we are going to study in lanthanoids and actinoids. But you will get to know that if they ask you, there's a very famous question. Lanthanum is a part of group 3rd only. Lanthanum is a part of group 3. Lanthanum is not a part of F block. Lanthanum is placed in group number 3 only. Actinium is placed in group number 3 only. Okay, everybody? Lanthanum. Thank you, Harsha, Lisa, Rasi, very good. Vimla, awesome, bacha, awesome. So tell me, lanthanum and actinium is a part of D block. It belongs to group number 3. But after lanthanum, we start filling F orbital. That is called as F block series. That is called as lanthanoids, right? So, and after actinium, you start filling. In lanthanum, we don't fill F block. In actinium, we don't fill 5F orbital. In lanthanum, we don't fill 4F orbital. In next to lanthanum, next to actinium, you fill these orbitals, right? So that's why we say, acha, F block is actually a part of group number 3 only. Because why? See, D block is called as transition element. D block elements, the elements that you see over here, they are called as these D block elements are called as transition elements, right? So if D block elements are called as transition elements, so simple fact is, if between the transition you have some elements that will be called as inner transition elements, that's why they are called as inner transition elements. But because inner transition elements, they are there apart, they are after lanthanum only, they are over here only, that is why they belong to group number 3. So F block elements belong to group number 3, right? Okay. Harsha, I don't want to be handsome. I want to be beautiful, yeah. Please don't call me handsome, yeah. Why I'm looking like a, am I looking like a man or something? You are calling me handsome, huh? Okay, understood? Yes. Now let's see. Now things will get very easy for you. They are placed in a separate panel at the bottom of periodic table. The name transition elements and inner transition elements are often used for these D and F block elements that I have told you why. There are mainly 4 series. Now let's jump back to D block elements. 4 series you have here, right? First series is 3D series, then there is 4D series, then there is 5D series, then there is 6D series. And each series, now out of this, the most important series is 3D series, which goes from scandium to zinc. That is your 3D series, right? Then after that, you have 4D, 5D and 6D series, and we'll talk about this in detail, right? Okay, we'll talk about this in detail, right? Now we are saying that in 5D series, lanthanum and hafnium 2Hg. Firstly, in 5D series, what you have? See, in 5D series, firstly here you have lanthanum, and after that you have hafnium, and this is Hg, right? This is a series. We can't say lanthanum to hafnium, because after lanthanum you have lanthanoid series. So you can't say lanthanum to hafnium. You can't say lanthanum to mercury is the 5D series. It is lanthanum, comma, hafnium to mercury. Similarly, the series that we call 6D series will be actinium, then this Rf to Cn. That is going to be the series, right? Okay. 2 series of inner transition metals, that is 4F. Now that will start from cerium to lutetium, right? And this thorium to this Lr, right? These actinoids, so we will not even study, because they are not, they are very, we'll see that why we don't study it, right? So that is your, this is your 4F series, that is F block and F block, that we are not going to focus here, right? Okay. Originally, the name of transition is derived from the, now why they are called transition elements? Because their chemical properties were transitional between S and P block. As we go from S to P block, there is a transition of metal to non-metal that you see. So that's why they are called as transition elements. IUPAC transition elements are defined as metals which has incomplete. Now this is a very important point, that transition elements are those which has incomplete D subshell, right? If it is D0 or D10, even in the excited state, that will be called as non-transition elements. And that is the reason a very famous question here, that zinc, cadmium and mercury of group 12 have D10 electronic configuration, right, in their ground state as well as their common oxidation state. Hence, they are not regarded as transition elements. So, zinc, cadmium, mercury are regarded as non-transition elements. It's a very famous question, and they belong to group number 12, right? That is the last group that you can see over here. You have zinc, cadmium and mercury, right? They are non-transition elements, right? Then, however, being end members of 4D, 5D, 3D, 4D, 5D transition series, their chemistry is studied along with chemistry in transition elements. That's why they are studied here, right? Otherwise, they are not transition elements, but they are studied over here. Okay. The presence of partly filled D and F orbital in their atoms make transition elements different from that of, because they have unpaired electron, they are highly paramagnetic. That is why they are different from the non-transition elements, right? Let's see. Hence, transition elements and their compounds are studied separately. However, their usual theory of valence as applicable to the non-transition elements can be applied successfully to the transition elements also. So we are saying that usual theory of valence as applicable to that valence electrons, that also you can apply here, right? That we have already studied in coordination compounds, that we will not study here. Various precious atoms like silver, gold, platinum, industrial importance like iron, copper, titanium belong to transition metal series. We'll study now, this is all like essay ही, right? Occurrence, general characteristics of transition elements, special emphasis on da 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 da. This will be followed by consideration. Okay, okay, this is all they are saying, that whatever we are going to study here, right? That's not at all important for you, so you can skip that, right? Okay. So now let's understand D block elements. First is we are going to talk about the D block occupies the large middle section of periodic table. In the middle it is between S and P block. The D orbitals, now what is this penultimate energy shell? Penultimate energy level are N minus 1 D orbital. N minus 1 is penultimate, right? So what we will see here, electrons are filled in penultimate shells, right? Of atoms receive electrons, giving rise to 4 rows of transition elements, that is 3D, 4D. All these series of transition elements are shown. Now let's talk about electronic configuration, very, very important, right? So the general electronic configuration, if you see, that is N minus 1 D. In D you are filling the electron from 1 to 10. In S you are filling the electron from 1 to 2. Sometimes in some books it is also written as N minus 1 D 1 to 10, NS 0 to 2, because NS0 exists in case of only one atom. That's a very important question. That exists only in case of palladium, right? That is PD. In case of PD, you have 0 electrons in s orbital. In entire transition element, there is no electronic configuration where you have 0 electron in s orbital. That's only one electronic configuration, that is PD. That's the only one. That's why this makes it very, very important. As you can see here, N minus 1 D 1 to 10, NS 1 to 2. Here you can see this over here, that PD, where its electronic configuration is 4D10 5s0, it's the only element where you have 0 electrons in the s orbital. It's very important. Next is the N minus 1 stands for inner d orbitals, which may have 1 to 10 electrons, and the outermost ns. See, simple thing is, when you have 3D, then you are filling the electron in 4s. So this is 4, so this will be 4 minus 1. Okay, so it is always going to be like that, right? So firstly you fill the electrons in 4s, then you fill the, because see, s orbital comes first. If you see here, s orbital is coming first. So firstly 1 electron, 2 electron, then third electron will go here, right? So that's how you will have 4s2, then you will have 3d here, then 3d electrons you will fill here, right everybody? That's how you're going to fill the electrons here. Let's see next one. Next is, okay, okay, they have 10, the outermost ns orbitals have 1 or 2 electrons. However, the generalization has several exceptions because of very little energy difference. Now this question is also very important, that n minus 1 and ns orbital has very less energy difference. That is why variable oxidation state, you will see manganese is a 3D element, right? And it shows like +2 to +7 oxidation state. So they can ask you assertion reasoning question, why D block element shows variable oxidation state? Because N minus 1D and NS orbitals, they have very less energy difference, that's why. Okay, so see, everything is written here only. That's why I'm telling you, questions are asked from here only. Here, so I have just started one page, and beyond this you will see really crazy questions which NTA has not asked you yet. But DNF block, I can guarantee that if you do from NCERT, no one can beat you. Furthermore, half and completely filled set of orbitals are relatively more stable. We know that D5 and D10 orbitals are more stable. Or this factor is, now we will see chromium and copper will have an exceptional electronic configuration. Let's see this over here, right? Let's see the, firstly let's study this table, right? In this table, what you're going to study, I'm not going to teach you like that, right? Okay, that's the benefit of when a teacher is teaching you NCERT, right? So I will not advise you to learn it like that. Rather, I will advise you, how do you remember? Firstly, you should know that uh, the series name, like how do I remember is Saktiv Karman Fikanika Jan, right? Now there are so many different mnemonics, you can make it yourself as well. Tiv Karman Fikanika Jan, right? Okay, then atomic number will be 21, 22, 23, 24, 25, 26, 27, 28, 29 and 30. Now bacha, what you will see here, just write 4s in all the cases, write 4s, 4s, 4s. Okay, you don't have to worry about anything, just write 4s, 4s, right? Then just write 3D everywhere. 3D, 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 3D. Let me see if I can copy this one, otherwise I'll go crazy, right? Okay. Okay, 3D, 3D, 3D. So this you have to little separate it. Put it over here, put it over here, right? Okay. That's how you have your 3D, 3D, 3D written, right? Now see one thing, what you're going to, how you're going to fill the electrons, let's see that. 2 1, 2 1, 2 2, 2 3, this is 2 4, okay, this is 2 5, just fill it as it is, 2 6, 2 7, 2 8, 2 9, now you can't write it 3 0 because 4s cannot have 3 electrons, so just write it 2 10, right? Okay, now see one thing, if you see here, this particular electronic configuration, what is happening in my home? Okay, so here if you see, in case of chromium, if you shift one electron, right, if you write it like this, 4s1 3d5, yes, because of half filled, this is more stable. Similarly, in case of copper, cancel this one, this will become 4s1 3d10, and these are the two exceptional electronic configurations of 3D. Okay, and this is not only useful in DNF block, this is useful in coordination compound as well. Without this VBT theory, you can't apply. This is useful in a very famous question that is asked, that is magnetic moment. You can only answer magnetic moment of 3D if you know these, if they are on your tips. You should know cobalt 27 4s2 3d7, nickel 28 4s2 3d8, manganese 25 4s2 3d. As it is, you should know this. This should be on your tips. Yeah, police is over there. I don't know what is happening, right? Even I have no idea what is happening. I'll have to go and, who has done what crime? Okay, so now we know that why copper and chromium, they are exceptional, right? Now, for example, consider a case of chromium. This is 3d5 4s1 instead of this. Why? Because the energy, very important, how the electron can jump. The energy gap between two sets, 3d and 4s, is very low, is very small enough to prevent electron entering the 3d orbitals, right? That's why electrons can go. Similarly, in case of copper, electronic configuration becomes this one, right? That's a simple case that we have studied here, right, everybody? Now, in case of 2D series, in case of 3D series, in case of 4D series, I'll just mention what are the important electronic configurations you should remember. Okay, I'm going to mention the important electronic configurations, guys, that you should remember. If you see this here, this is Okay, here first is PD is very important because PD has 4s0, sorry, 5s0, 5s0, 6, 5s0, 4d10, right? 5s0, 4d10, that is PD is very, very important, right? You know what? You can also write down the exceptional electronic configurations here as well. I can just draw a simple, because this PDF though I am going to provide eventually. I'll just write in 4D series what are the important electronic configurations that you should, like, you cannot skip that. First is PD, that is 5s0, 4d10. It is very, very important. Then guys, if you talk about this Y, ZR, NB, here you can see exception, 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 right? Okay, here also it is exception because 5s has only one electron, that means this is something exceptional. Okay, here also you can, in most of the cases it is exceptional. Okay, so it is supposed to be, 1 2, I'll just tell you how to remember this. Okay, it is supposed to be 1 2 3 4 5 6 7 8 9 and 10, but everything has changed. First two has same, till zirconium you have okay, right? Okay, till zirconium it is 2, so it's like good enough for you, right? But after that you will see like, ma'am, what is happening here? Ma'am, in NB you have 4s1, 5s1, MO you have 5s1, TC you have 5s1, right? RU 5s1, RH 5s1, AG 5s1. That means it was supposed to be 1 2 3, this because one electron jumped, so this shifted 4. This is supposed to be 4. Okay, I'm just going to write it here. This is supposed to be 3 electrons in 4D, 4 5 6 7 8 9 10. Okay, now see what happened. Because one electron shifted here, this became 4. One electron shifted, this became 5. One electron shifted, this became 6. One electron shifted, this became 7. One electron shifted, this became 8. Right here, 2 electrons shifted, so instead of 8, it became 10. Here again, 1 electron shifted, it became 10. Understood how to remember this? I am giving you a simple way of understanding this. Okay, simple way of remembering this, guys. I am giving you a simplest way possible to remember this. Right, remember that from NB to RH, you have 4s1. In AG, you have 4s1. So you will add 1 1 here, like whatever you had, you will add 1 1 here, right? Okay, but in the case of 5D, right, when you talk about 5D, right, 5D electrons have, this was the 4s1 we talked about, so 5D electrons you will add 1 1 here. In the case of PD, that is most exceptional, where you have 5f0, so instead of 8 you will have 2 here. Okay, understood everybody? Better tell me, clear, right? Understood? Now maximum 3D or 4D series, they can ask you. 3D is very important, you must know it, right? 4D you should remember the exceptional things here, right? Then if you talk about 5D and 6D, as such they don't ask you that, right? So you can skip that as well, right? Otherwise some important, if I say let's talk about some exceptional, like PT is exceptional, that you must remember, right? Then RG, that is exceptional, that you must remember, because only exceptional only they will ask you if they ask you, right? Otherwise they are not going to. Like this one is least chances. Your 4th series, that is your 60 series, has least chances that they will ask you that. 3D, 4D, 3D should be on your tips. 4D series you should remember, because there are so many exceptions, they can ask you that, like high probability, right? 5D series only one platinum, just understand that. 6D you don't even need to remember this Rg. If you don't remember, that is also okay, but yes, you should remember that, okay, this has only one electron, other has 2 electron in the s orbitals, right? Okay, that is what you should remember. This is what I tell you, that you should know from the tables and all. This is the things that you should be able to understand from the tables, right? Now, if you see zinc, cadmium, mercury, we know that the electronic configuration are always 10 electrons, right? That is why they are always completely filled, even in the ground state or the excited state. That is why they are regarded as non-transition, not regarded as transition elements. That means they are non-transition elements, right? The d orbitals of transition elements protrude to the periphery of an atom. We are saying d orbitals of the transition elements protrude to the periphery of an element more than the other orbital. It means s and p orbital, hence they are more influenced by surrounding as well as. Now this is a very important point that they have asked already in a statement based question, where students got confused, ma'am, what they are talking about. So actually, if you see, d orbitals have this kind of shape. They have this kind of shape, that is double dumbbell shape. So that is why they are more expanded. Periphery of the atom is towards the end of the atom, they are more. That's why they are more exposed to the outer environment. That's the reason. Now they are more exposed to the outer environment, they are more influenced by the surroundings. That's the reason they are more influenced by the surroundings, right? As well as affect the atoms or molecules surrounding them, right? In some respects, ions of given d n configuration have similar magnetic and electronic properties, right? So that's why if you talk about uh, first two things we have discussed about d elements till now. First is n minus 1d orbitals and ns orbitals, they have same energy. That's why electrons can shift. That's why they show variable oxidation states. Second statement is that they influence the surroundings and they also get influenced by the surroundings, right? And that is the reason they also show similar kind of properties with each other. Also they show kind of similar properties. With partly filled d orbitals, these elements exhibit certain characteristics properties such as display of variety of oxidation state. Now they have D1, D2, D6, D7. That means D0 and D10 configuration is very less. So that's why they show so many properties, and that we're going to study in detail. First is variety of oxidation state. Second is formation of colored compound, that we will see, because colored compound, so many questions are based on that. Entering into the complex formation, they form complexes. That's why in coordination chemistry you will see only D block elements there. The transition elements and their compound also exhibit catalytic properties. Also they exhibit array catalytic, they behave as catalyst. In Haber's process iron, in you have Ziegler-Natta catalyst. Towards the end of the chapter you have proper applications, and from their catalytic property they ask you match the following question: which catalyst is used where, which catalyst is used in contact process, right? So these things we are going to study towards the end of the chapter, right? Okay, all these characteristics have been discussed later in this chapter. There are greater similarities in the property of transition as we move in a horizontal row, as we go from group 1 to group 2, group 3 to group 12. They show similar properties in contrast to non-transition elements. However, some group, non-transition means we are talking about when you go in a P block, when you go period wise, right? The similarity in the properties will be less. But in D block elements, the similarity in the properties will be more. Again, what is the reason? N minus 1 D orbital and NS orbital are very same. They have very same energy. They are because of their less energy difference. We shall first study the general characteristics and their trends in the horizontal rows, particularly 3D row, then consider group similarities. So that's how we study this, right? Okay. On what ground can you say that scandium is a transition element but zinc is not? Similar. Scandium is what, guys? Scandium is 4s2 3d1, 2 1. And zinc is what? This is 4s2 3d10. Even if you take electrons from here, scandium 2 positive, scandium 3 positive, fully filled electrons are not there. Completely filled orbitals are only there in case of zinc. Whether you talk about zinc or you talk about zinc 2 positive, which is actually uh, only 3d10, that also has completely filled orbitals. So that is the reason that it is non-transition element, right? Now this is another question that is an in-text question, that is, silver atom has completely filled d orbitals in its ground state. However, can you say that it is a transition elements? If you see what is the transition, what is the electronic configuration of silver, right? This is silver, right? It is 5s1 3d10. Let's write it over here, right? Silver is 4s1, no, it is 5, it is, wait a minute, it is 5s. Silver is 5s1, wait a minute. Silver is, let's talk about that. Silver is 5s1 4d10, right? If you say silver takes out electron, then it will become 4d10. Further, if you take silver 2 positive, then it will become 4d9, right? So we can say in its excited oxidation state, it does not have fully filled, and transition elements are that in the excited state also they should have, uh, that means in excited state also they should have like complete d orbitals. If you say silver 2 positive, that is not complete d orbital, that is 4d9. That is why it is transition element. That is why it is a transition element. Okay, let's talk about next one. Physical properties, general properties of d block elements. Now because they are metal, so they will show all the properties of metal. Now firstly tell me, what is high tensile strength? What is a tensile strength? Its ability not to get break easily, right? It has a good ability, it has a good strength, right? You pick up a copper coin, you can't easily break it, right? Tensile strength is good. Ductility means its ability to get converted into wires, right? That's why you have copper wires. Malleability, that means like you have gold sheets. You know, Rutherford experiment, we have used gold foil experiment, it is called gold sheet. Gold is what? It's a transition element, right? So it is very thin sheets, it can be converted into. High thermal and electrical conductivity, right? That's why we will see in kitchen the alloys of these transition elements are used in our daily life. Because why? Because heat conductivity is there, electrical conductivity is there. That's why copper wire are used to, you know, conduct electricity, that they are used. They have metallic luster, they have a good shiny luster like a metal, right? Because they are metals, right? With the exception of zinc. Now let's see one thing, very important point is written here: zinc, cadmium, mercury, and there is one more thing, manganese. They have one or more typical metallic, very, very important thing. We ignore these lines. We totally, we're like, okay, physical properties, ma'am, this is never asked. Ma'am, jump to next one. But they ask you questions from here. What question they will ask you? Very simple question directly written in your NCERT. If you can see from the table also, it is mentioned cross here, zinc, manganese, right? I'll just mark it here. Zinc, manganese is cross, then cadmium is cross, then mercury is cross. Can you see that? Zinc, cadmium, mercury, right? If you want to make a big cross here, I can make that as well. Okay. Array. See, manganese, right? Manganese, Which is the pen that I should use to make? Manganese, zinc, cadmium, mercury. These four elements, they don't have typical metallic structures. Like if you see, vanadium has typical structure, right? Titanium has typical structure, hafnium has typical structure, right? But in case of, it's not like they don't have any structure. They have structure, but it's not a typical metallic structure that they have, right? So this, all these cubic center, body centered, face centered, hexagonal, all these things will study in solid state. So that much they will not ask you from here. They are going to ask just one thing. With the exception of zinc, cadmium and mercury, they all have typical metallic structure, right? So whenever exception is there, let me make a pen which I will use for all the exceptions. Tell me which pen I should use, which can also, give you a hint that some exception is coming over here. Should I use black pen? Which pen should I use? Ma'am, tensile meaning capability. Yes, definitely, Krishna. Tensile means capability, ability to stay intact, right? It's strength, right? Okay, yes. Okay, what are the chit chats going on over here? Message, retract, I can see over here. I don't know, maybe, chalo. Okay, tell me. Right? Pink pen you want me to use for? Beta, pink pen. Pink pen you want me to use for that? Chalo, theek hai. Okay, fine, I'll use that then. Right? Pink pen is for all the exceptions in this PDF. Right? Whenever there is exception, till now where we saw exception, I saw exception here, right? That is big exception over here, right? That was the biggest exception, right? Okay. Purple, here purple I think would be better. Let me use purple. Don't you think so? Purple is better. It's actually seen, actually. I'm able to see the difference. Or we also have other pens here. We also have yellow pen is not visible only. Yellow I can keep, but it's not visible only. Red I have used so many times in different places. So which one? Pink only. Okay, chalo, theek hai. I'll just make it little darker because I think this is better. Yeah, this one is better. So I'll just use it for all the exceptional things that we have done till now. This one is the exception, that is important exception, right? Wherever you have like super duper important exception, there I'll mark it, okay? So here you have super duper important exception, zinc, cadmium, mercury and manganese. They don't have typical metallic structure. They can ask you out of the following which has typical metallic structure, right? So except for all these, everyone has typical metallic structure. Let's see. Next is the transition elements, metals, with the exception of zinc, cadmium, mercury, are very hard. Now, which is the exception? Now we are saying that the exception is zinc, cadmium, mercury. Except for zinc, cadmium, mercury, they are very hard. So that is also another exception that you see over here. Zinc, cadmium, mercury are not hard. They are under the exception, right? Transition elements are very hard and they have low volatility, but the exception is zinc, cadmium, mercury. The exception is zinc, cadmium, mercury, which are going to be, very important thing it is, they are going to be soft plus volatile. So that's why they are also called as volatile metals, right? Because they have good volatility. They can get easily volatile. They can get converted to vapors easily, right? Mercury is it is existing at room temperature in liquid only, right? So that's why. Next is a very hard, low volatility. Their melting and boiling points are high, right? Their melting, this is just general point that their melting and their boiling points are high, right? Depicts the melting point of transition element belong to 3D 4D series, right? So 4.1 will see the melting points. We'll actually study this graph also, because from this graph as well the questions can be asked, right? Depicts the melting point of transition elements belonging to 3D. The high melting point of these metals are attributed to involvement. Why they are having high melting point? Reason is of these metals attributed to involvement of greater number of electrons, from n minus 1d in addition to ns electrons in the interatomic metallic bonding. In the metallic bonding, they have more greater number of n minus 1d orbital, that is electrons. That is why they have very high melting point, right? In any row, the melting point of these metals rise to maximum. They will rise to maximum at D5. This is very important, that they will rise to maximum. Metals melting point rise to maximum at D5. If you see at D5, they will rise to maximum, right? Like you have this chromium, molybdenum, tungsten, right? So they can ask you which out of in 4D series, in 3D series, 4D series, 5D series, which has the highest melting point. In 3D it's chromium, in 4D it's molybdenum, in 5D it's tungsten, right? So that's why tungsten is used in bulbs, right? Okay. Now exception is that except for anomalous value, that means weird values, that is not understandable, right? Values of which one? Values of manganese and technetium, and falls regularly as atomic number increases. Now they are saying, firstly, what is the criteria? Criteria is till D5 it will rise to maximum, that then it will decrease. Criteria is till D5 it will rise maximum, then it will start decreasing, right? That is the simple general trend. But what we saw that after chromium you have manganese, so it should be like this and then it should decrease. But actually a weird trend, a weird exception that I am marking by this pink color here and this technetium over here, right? Okay, they are regarded as exceptional behavior, because suddenly you will see a anomalous behavior where they are showing a drop, right? So in TC and MN they are showing a drop. That is the exception here. Otherwise they will rise to D5 and then suddenly decrease, like what is happening here. They are rising, then they are decreasing. But in this case they are rising, then decreasing, then again rising and then decreasing. So these two are regarded as the exceptional cases, right? Okay, right everybody, except for anomalous values of TC and MN, right? So I'll do one more thing here. I don't know if you will like it or not. This is better now. This is better now, me highlighting it already. I forgot that I have highlighter as well. Exception of zinc, cadmium, mercury, they are not hard. Then this is another exception, and this is also exception of zinc, cadmium. This one or more typical structure at normal temperature they are not showing. Okay, yes everybody, tell me. I'll just write down the important electronic configuration as well, right? Okay, any problem everyone? Any problem? Yes. This is better, no? Highlighter I think is much better. You will feel like, okay, we are doing this, right? So, next guys we have fall regularly as atomic number increases. They have high enthalpies. Now this is very important, enthalpy of atomization. High enthalpy of atomization they have very high enthalpy of atomization, right? which are shown, we'll see that the maxima at about the middle of each series indicate that one unpaired electron per d orbital is particularly favorable for strong interatomic interactions. More are the interatomic interactions, more will be the bonding, high will be the melting point. So in the middle, in tungsten over here, because you are saying that maxima it is reaching over here, that means it needs more the number of unpaired electrons. So can I just write it here? Number of unpaired electrons will define the melting point. Can we write the crux here? Right? The maxima at about middle of each series indicate one unpaired electron per d orbital contribute to more interatomic interactions. So that is why number of unpaired electrons will tell you the melting point, right? In general, greater the number of valence electrons, stronger is the resultant bonding. Since enthalpy of atom, now let's understand enthalpy of atomization. Enthalpy of atomization is same as melting point. So when the interatomic interactions are strong, then to break that into different atoms is also different. So since enthalpy of atomization is an important factor in determining standard electrode potential, when we will calculate standard electrode potential, you will see that enthalpy of atomization is very important factor in that, right? So metals with high enthalpy of atomization, very high boiling point, tend to be noble in their reaction. Ma'am, what they just said? So we are saying metals, right? Metals with high enthalpy, which has very high enthalpy, with a very high boiling point, they will have tend to noble in their reaction. They will not react because they very high energy is needed to make them react. Enthalpy of atomization is very difficult. For example, so many atoms are there, you want to break all the bonds here. Then if the enthalpy of atomization is very high, it's very difficult to break the atoms, to take out the individual atoms, and that's why they will not react that much, right? So high enthalpy of atomization, that means they will be very noble in their behavior, like noble in their reactions, right? That we'll study later on. Another generalization that may be drawn is that metals of the second and third series. Now we are saying another generalization is, if you talk about this is delta H atomization only. Now we can see this is 3D, this is 4D, and this is 5D series. So what we can see here, that as we go down in the series, right, then the enthalpy of atomization increases. So that is why 5D, 6D are very like noble in their behavior. We don't even study that, right? So greater enthalpy of atomization in corresponding to element of the first series. So we can say that it actually exists like this. Firstly, you will have 3D minimum, then 4D, then 5D. That is going to be the order of enthalpy of atomization, right? That is going to be the order of enthalpy of. This is an important factor in accounting occurrence of much more frequent metal-metal bonding in the compound of heavier. Now, because see, they are not interested in making like these are atoms, right? Now what you will see, because if it is a metal of 3D series, you can, it still has less enthalpy of atomization, so you can break the bond, right? And this, let's say I am having cobalt. Cobalt, I can see so many complexes of cobalt, right? But let's say this particular metal is from 6D series or 5D series. In the heavier elements, that means down the group size increases, so they are heavier. In the heavier elements, right, they don't want to break because the energy that you are giving them to break the bond is not that much. The energy is very less that you are giving them. So that's why they are like, why will I break the bond? So you will see metal-metal bond are too much here, because metal-metal bond we are not able to break. So that's why they are saying that it's important accounting that occurrence of more frequent metal-metal bonding in compounds of heavier metals, Because of their high enthalpy of atomization, the metal-metal bond you are not able to break, and that is why you will see metal-metal bond there, right? Okay, understood? In heavier elements, you will see metal-metal bonding, right? In heavier elements, you will see metal-metal bonding. Achha, now before going in the ionic size and all, we shall firstly study this particular thing, that is very important, enthalpy of atomization, right? Because this they have asked in recently, they have asked it, right? They have recently asked this in JEE 2025. They have asked a question where they said a metal which has maximum enthalpy of atomization. Now the one who don't know like which metal has maximum enthalpy of atomization, they will be like, I don't know about this thing. They will skip the question, right? So same question they can ask you in NEET as well. That's why to understand this, otherwise the order is quite weird, right? If you're here JEE aspirant, then I would say you should remember the full trend of enthalpy of atomization. It is nowhere given in NCERT. It is only given in the form of table, right? So I will write the full trend here. Maximum you will see is for vanadium. So that's why the answer for that was vanadium, which has maximum enthalpy of atomization. And minimum you will see is for zinc. So these two things though NEET aspirants also should remember. That maximum is for vanadium, minimum is for zinc, right? This much though you must remember. And if you're not remembering this, that means not interested in having good marks. Vanadium, acha, after vanadium what you have? 500, 400 I am looking for, that is titanium, right? Then after 473, you have again 400, this one, this one, this one. And yes, out of these, you have maximum is this one, that is nickel. Then you have cobalt. Then you have iron, right? Once this is also done, then what you will have here? 300, that is this one, and this one. So 397, that is chromium, right? After chromium, bacha, you will have copper, right? After chromium, you will have copper, right? You can also write chromium like this. After chromium, you will have copper. Then you will have, after copper, you will have scandium, right? After scandium 326, what you will have? 281, that is manganese. Let's see if 10 are completed or not. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So this is the order. Recent interest we can see here. NTA is interested in this in recent year. And in recent year, NTA is like, okay, I'll ask students highest enthalpy of atomization. Nowhere in NCERT, in any theory part in the lines it is written. It is nowhere written. It is written over here in this table that students usually skip, right? Okay, so reading NCERT is this. Reading NCERT was not like, okay, this I have studied. That is not reading NCERT. Reading NCERT is this one. So maximum you must remember, guys. Maximum enthalpy of atomization is of vanadium and minimum is of zinc. These two things so you must remember. Order, I really doubt that they will ask you the order, but maximum and minimum they can definitely ask you. And second maximum you can say the runner up is titanium. After that you have nickel, vanadium, titanium, nickel, and least is for zinc. Okay, this much you must know, right? Everybody tell me if there is any problem here, right? Because now we are going to start with atomic and ionic size variations. Tell me, guys, if there is any doubt till here, right? Is there any doubt till here, everyone? Any doubt you have, then do let me know. And have you liked the session or not? Let me see. How many of you have already liked the session? How many of you have not liked? Ma'am, I will not like the session. Ma'am, you do whatever. Ma'am, we want you to go again. Right? Then ma'am will not come back. Right? So, like this session, right? Because we also feel very happy, right? When you appreciate us. Right? Clearo. Yes, everybody. Done, done, and done, done. Let's move towards the next chapter. Lisa, Shravas, Guru, Baswaraj. Guru Baswaraj. Is this on the name of Baswaraj, sir, or this is your name? Are you saying my Guru is Baswaraj, sir? Right? Very good. I can see your energies over here. Awesome, everybody. And who are those silent students who are sitting here? I want their energy as well over here. I want your energy as well, guys. And do you promise me, if you just watch one lecture of the series, missing out on something really, really important, right? Right? So you have to watch the full part here, right? Okay. Like if you're promising yourself, I will not even, DNF block and P block, ma'am, I'll do thoroughly with you. Then you have to be like with that commitment. It's like once I do the commitment, I don't even like listen to myself again, right? So if you think that yes, we are going to do, so we are going to do that, right? Okay. Okay, Baswaraj. Awesome. So let's see this. Variation in atomic and ionic sizes of transition metal. Let's see that. In general, what we are saying, in general, ions of same charge in a given series show progressive decrease in radius. In general, what we see, there is decrease in the radius because along the period size decreases. So in general, it should be decrease with increasing atomic number. This is because new electron enters a d orbital each time the nuclear charge increases by unity. New electron is being added, nuclear charge is also increases by unity. So for example, this is 3d1, this is 3d2. Nuclear charge has also increased by unity, so attraction is more, and in the same distance you have added one more electron, so that will be attracted easily, right? So that is the reason, just like we have discussed in periodic classification, and that's why along, this is simple thing, that along the period, in general, atomic size decreases, right? Okay. Now we are saying that it may be recalled that shielding effect of d electrons is not that effective. Now we know that what is the trend of shielding effect? Tell me, what is shielding effect? Shielding effect is protection. For example, here I say that this is the nucleus and these are the electrons. These are the electrons that I have, right? So when I say these are electron over here, and this is some outermost electron that is there. So if the inner core electrons that you have over here, if the inner core electrons are able to shield, protect the outermost electron, that is this one, from the nucleus that is positive, then we can say that definitely they have good shielding effect, right? If they are not able to protect, then the electron will get attracted, right? Electron will get attracted, it will get attracted, and the size will shrink here. The size will decrease. That means it depends upon the shielding effect. And if you say the shielding effect of which one is good and which one is bad, the shielding effect, if you remember this from periodic classification, the shielding effect of S is maximum, then P, then D, then F. That means F orbital, they don't have as such a very good shielding effect, right? That means these d orbitals, they don't have a good shielding effect. So that's why when you're filling the electrons, you have 3d1, you have 3d2, you have 3d3, Similarly, let's say here you have proton P, here you have P plus 1 proton, here you have P plus 2 proton. So adding, nuclear charge is increasing. So nuclear charge is the inner core electron charge is increasing, increasing, increasing. And d orbital is at this much distance. Let's say it like this, okay? Okay, let's think about this like this, okay? So here you have nucleus, right? Here this is the outermost d electron, right? Inner core, so many electrons you have, right? And this is 4s orbital. This is 3d, okay? This, let's say, is 3d. Let's say this is 3d. This is 3d. This is the electron that you have over here, right? 3d electron you have. If you have, let's say 4s, you have one electron here, right? In 3d, let's say you have one electron, then in 3d you have two electron, then in 3d you have three electron, then in 3d you have four electron. Now this 3d is under the shielding. It is actually shielding the outermost electron, because this 3d orbital, right, that does not have a good shielding effect. So whenever you are adding the electron, it is not showing a good shielding effect. That is why this 4s, this size is eventually decreasing only. The size is eventually decreasing only, right? Okay, because the charge is increasing. Charge here is increasing. 3d does not have a good shielding effect. So outermost electron will feel the attraction. That is why this will happen, okay? So shielding effect of d orbital is not that effective. Hence the net electrostatic interaction between nuclear charge and outermost electron increases and the radius decreases. This is in general, we are saying that radius should decrease, right? Okay, ma'am, when live for JEE channel soon will be there, right? Don't worry, right? Don't worry, I'll be there. Don't worry, bacha, right? So that's why I thought that by the time, right, I should, complete some some different series that JEE aspirants can also watch here, right? Okay. So, because this thing I have not done on JEE as well, right? So that will be beneficial for both the students, right? And that's why, right, I try not to repeat the things on both the channels so that both the students can get value, right? Okay. The same trend is observed in atomic radii of given series. However, the variation, we are saying the variation within a series is quite small. The variation that you will see is very small. Atomic radii of given series. Okay. An interesting point emerges when atomic size of one series are compared to with those of corresponding elements of other series. The curves show an increase from 3D to 4D, but the radii of 5D are virtually same as that of 4D series. Why so? Let's firstly talk about that. Okay, firstly let me just put in this particular point here that is important, that 4D series, third series, they have same radii as second series. That means we can say from this particular line 4D and 5D series, they have same size. Okay, and that's why zirconium and hafnium, they have same size. Now what is the reason behind that? Let's talk about that. That is based on shielding effect only, right? Okay, now for that you have to go over here, right, that we have discussed here, right? So we discussed that in case of lanthanum you will add only this is 3D, 4D, 5D electrons. In actinium you will add only 6D electrons, right? But can you see from 4 to 12 period, in Very important thing I am writing. In 3D, 4D, 5D. In 5D series, from group 4 to group 12, okay, what we are saying, wait a minute, let me just write that again. In 5D series, group 4 to group 12, we add 4F in 5D series, and I am not doing that in group. This is a very important thing, that we are not adding 4F in group number 3. We are not adding 5F in group number 3, right? From group 4 to group 12, you are adding, we add 5F, right? What we add is 5F. Okay, ma'am. Done, ma'am. We add that, ma'am. Now what? Now when you're adding, this is actually zirconium, right? Now when you add here 4F, here 4F, in all of these cases we are adding 4F. Here all these cases we are adding 5F, right? And if you remember, we have discussed that 4F has poor shielding effect. What we have discussed? 4F, if you're talking about the shielding effect, what I told you, shielding effect, guys, shielding effect of S, then P, then D, then F. F has very poor shielding effect. So 4F has poor shielding effect. So what will happen in this case? So if I say that here you have a like nucleus, you have so many electrons here in between, 1 2 3 4 5 6, and over here you also have 4F, okay, you're also adding 4F here, right? Then there is some outermost electron that is there, right? Outermost electron that is there. Now you know what you will see here? You will see that here you will also had somewhere 3D also, here you have 4F also. 3D had poor shielding effect, but 4F has even more poor shielding effect. That is why this will start decreasing the attraction of outermost electron and the nucleus. What we are saying? The attraction of this particular nucleus and the outermost electron, it will be very high. The attraction you will see will be very high. Because of this attraction over here, what will happen? Because of this attraction, the size is going to decrease. Okay? Size decreases. That is because that is contracted, and that is contracting because of lanthanoids. Because here what you have, in before hafnium you have lanthanoids. That is why it is called as lanthanoid contraction. Lanthanoid contraction. Tell me, is that clear, everybody? Yes. I'll teach aldehyde ketones and carboxylic acid after that. Okay? Yes. So everybody, do let me know, is that clear? Is that clear, students? Works? Everybody. Tell me, everybody, is that clear? That works for all of you or not? Right? Let's go again to the same part where we were. Oof. Yes. We were here. Wait a minute. Okay. Yes. So, we were here. This phenomena is associated with intervention of 4F orbitals, which must be filled before 5D orbitals elements. The filling of 4F before 5D results in regular decrease because of lanthanoid contraction, because of poor shielding effect of 4F orbital. which essentially compensates for the expected, and that is the reason, if you see here, over here, what you will see, that is the reason this is nothing but this is 3D, this is nothing but this is 3D, 4D, 5D and 6D, because this size of this is decreasing, this decreases, so it becomes similar to 4D only, right? That's why we are saying that lanthanoid contraction makes 4D and 5D series have the same approximately same atomic radii, that is the consequence of lanthanoid contraction. Okay, that is the consequence of lanthanoid contraction that we are talking here, right? Okay, tell me everybody, is that clear? Is that clear to all of you or not? uh Hello. Okay, yes everyone, now am I audible? But the poor thing is that I don't have like, this is, I'm not able to attach it to this one, right? So I'll have to hold the mic. Yes everybody, tell me, now there is voice? Yes everybody, voice is there, everyone? Yes students, ma'am has not gone anywhere guys, I'm here only, right? Just give me a second. Okay, So there are two problems here. What are these two problems? First problem is that our iPad is getting has only 35% charging. Second problem is that our mic is getting charged. So there's two little problems we have. So what I'll do is, shall we take a break? How many hours we have been studying? It's not that much, no? We can study for like two more hours. Is it? Do you have that capability? Uh, Otherwise, this will be divided into too many parts. That I don't want. Right? If it is divided into too many parts, then again, if someone is watching it on the recorded version, it makes a chaos out of that. Right? Okay. So we'll take a break of 10 minutes. After 10 minutes, I'll give you the break of 10 minutes, right? So that, chalo, after 5 minutes, I'll give you the break, right? You can also relax a little bit, right? And after that, we'll join the session again. Okay. Now, if you see this here, guys, we are saying that imperfect shielding of 4f orbital is the reason that we are not able to, the size is decreasing entire 4f also. In 4f orbital also, in lanthanoids also, you will see the size will decrease. That will study in lanthanoids. The decrease in metallic radius coupled with increase in atomic mass results in general increase in density of these elements. Now, Bacha, tell me one thing. What is density? Can you tell me what is density? Density is equals to mass by volume, is it? Yes, students, tell me what is density? I should just write it over here where we are talking about density. Density is equals to what? Mass by volume. Am I correct on that? Density is equals to mass by volume. Now, volume is nothing but volume is 4 by 3 pi r cube for an atom, right? So that means it is directly proportional to mass and inversely proportional to radius. Radius is decreasing, so density will increase. Mass is decreasing, atomic mass, we are saying increase. When we are adding the electrons, we are adding the protons, mass will definitely increase, no? Mass will increase when you're adding, when atomic number is increasing, mass will also increase. So mass will also increase. So whether mass increases or radius decreases, that results in the increase in the density. Now, ma'am, is there any weird order, ma'am? See, enthalpy of atomization you have seen here. Right? Ionization enthalpy we have not discussed till now. Let's study density. Density, if you see here, density is, it should increase, right? So 3.4 to 4 to 6 to 7 to 7.2, 7.8, 8. So we can see one weird thing here. Can you see one thing here? That is not, can you see it is not written anywhere? It is not written anywhere. Here they have not written this to copper, the significant increase in, they have not written that after copper it will decrease. They have just, if a student is, reading the NCERT, is like, okay, density increases. They ask that copper has more or zinc has more. Which has more density, copper or zinc? You will say, okay, it increases, so zinc will have more. Answer wrong. Right? So, this is why NCERT reading along with tables is important. You need to check the data as well. We can see that the density of nickel and copper is same and zinc decreases. Zinc is even less as compared to chromium. Chromium is what? 7.9. It is even less than chromium. Right, so after copper here, I'll just write down that there is some exception over here so that you can remember this, that this is the exception that we see here, right? Firstly, if you see till here it is increasing, then it is, these two are same. This is NCERT data. right? Latest NCERT data only. Ma'am, it is to remember. No, no, no. Values you don't have to remember. Values nobody is asking. Values you don't have to remember. Just see the data here. That okay, from here it is increasing, and nickel and copper, they have same density. Nickel and copper have same, and here you will see there is decrease, and decrease is not very less, very high decrease is there. 8.9 to slightly 1.7. It is so less that this is active कर. Chromium has more as compared to zinc, right? Okay, less than zinc. Less than zinc are, what are the densities which are less than zinc? Suctive. They only have less than zinc, other have more than zinc. These are the only three elements which have densities less than zinc, others have more than zinc. Then firstly you will have, that means the order will be scandium, titanium, vanadium, then you will have zinc. In between you will have zinc. That's why I am writing it as an exception. In between you will have zinc out of nowhere, right? Suctive, then you will have kar, man, fi, ko, ni, ku, jan. Okay, right? So that's a weird thing that you must remember. So rather than this, I'll just write this thing here, that here you will have decrease. Okay, that is mentioned in this particular order. This is the increasing order. Achha, zinc will not be there na. So this is the increasing order, right? This is the increasing order. Increasing order of density. It is nowhere mentioned directly, but indirectly it is mentioned. Okay. Yes, everybody. Achha, standard electrode potential we have not discussed till now. We will discuss it, and we'll have to discuss it in like really in detailed manner, right? Then guys, let's talk about metallic and ionic radius. Enthalpy of atomization also we have not discussed till now. If you see the ionic radius, can you see 64, 47, 35, 29? Then again it is increasing, right? So that means there is some trend is not like very smooth. It is decreasing, then again it is increasing, then it is decreasing, almost similar. Can you see here? Can you see here, guys? Metallic trend here, right? It is not a same trend that you expected. This is scandium T V kar man fi ko ni ku jan. Now I want to write the trend of radius here. Trend of radius according to the data that is given. And please never, maybe in other books you will see a different trend, but always remember trend of NCERT is only the trend that you should follow, because little bit differences can be there, but eventually if let's say you have answered it according to NCERT, you can even go to the quote and say in NCERT this was written, right? Because in the end, what is written in the NCERT, that is the main thing for NTA, nothing else, right? That you should remember. So now if you see here, firstly scandium, its order is decreasing, then titanium, then you have vanadium, then you have chromium, then suddenly increment is there, right? That means suddenly you have increase, that is manganese, it increases a little bit, right? So increment is there of manganese. Scandium to chromium, it is decreasing, here it is decreasing, then suddenly there is increment in manganese, and then suddenly also it starts decreasing, right? Then you have iron and cobalt and nickel. They are approximately same. Can you see? They are approximately same. This is according to the NCERT data, right? In some books it is written at firstly it is decreases, then it is same, then it increases. Now here the value is given that it increases, so I'll take that value only, what is given here, right? Now here they have given copper, cobalt and nickel to be exactly same, right? Then it will increase again, it will increase, that is copper and then zinc. Now if you see manganese and zinc is approximately same, so rather than writing it like this, you can also write it like this. Wait a minute. You can also take this here, right? You can also write this that chromium and iron. Chromium has more as compared to iron, then it is same, copper, zinc, and zinc is same as manganese. This is from the data of NCERT that I am writing. Okay, this everything that I have written here is based on NCERT data. I am not making this up. I am not writing this from some other book. If they ask you this much detail, then surely you are going to define it according to the NCERT data only. You don't need to write any other book data here, right? Okay. Now let's see, if you see this over here, then manganese increment is not mentioned in the graph, but in the data it is given, right? So usually in most of the books you will not see the increment in the manganese. You will see firstly it decreases, then it's same, then it increases, that's it, right? That you will see, right? So firstly it is decreases, then it is same for iron, cobalt and nickel, right? Cobalt and nickel, it's a, like totally same, right? Then it increases here, right? And manganese in reality if you see the data, manganese is actually here, so it is actually like this. Okay, it should be mentioned like that because it is written in the data, right everybody? Okay, but in most of the books we don't mention manganese. We'll just say decrement, then same, then increment, that's it. Okay, and we have seen that why this happens. I'll just tell you why. Here I'll write it. Scandium to iron, or you can say, yes, iron you can write. Why the size is decreasing? Because Z effective is actually more than the screening effect. Screening effect is not that high, right? Then cobalt, nickel, why it is same? Cobalt and nickel, why it is same? Because Z effective is equal to screening effect. And zinc to copper, it increases because Z effective is less than screening effect. Screening effect dominates, the screening is very high, that is why the size increases. Okay, that is the reason behind this. And here you will see one more thing, that this is 4D and this is 5D and this is becoming approximately same. The difference in 3D and 4D is very high, but 4D and 5D you will see they are almost overlapping each other. Reason being lanthanoid contraction. Right everyone? Okay. Why do transition elements, they exhibit high enthalpy of atomization? Because large number of unpaired electrons, they have stronger interatomic interactions, that is why they have high enthalpy of atomization. Highest enthalpy of atomization is there in which one? Yes everybody. C. Then students say, ma'am, I don't know ma'am, in the exam they asked which one has the lowest enthalpy of atomization, ma'am. That was not written in NCERT. What is written here in the question form? Enthalpy of atomization of zinc is lowest. Okay, this you must remember. Enthalpy of atomization of zinc is lowest. It's very important thing this is. Okay. Highest is vanadium. Right now guys, I'll give you break, right? Because after this we are going to study like really, really important things. Electrode potential, oxidation state. Then we are going to study ionization enthalpies. All these things we'll study after break. Okay? Right, everyone? Tell me about it. Okay? So I'll see you all after the break. By that time, what I'll do, I'll just pause the screen on this page only so that my iPad also can get charged, right? And without any hurdle, we can do rest of the lecture. Okay, everybody? So let's have a break. I'll see you all at what's the time? I'll see you all at what time? Tell me. So I'll see you all at 5. What? Class will resume at 5:15. I think that will work. Or 5:20. है ना, थोड़ी सी चार्जिंग तो my iPad needs. So I'll see you all at 5:20, okay? I'll see you all at 5:20 p.m. You can also take rest. You can also relax so that we can do the rest of the class at 5:20 p.m. Class will resume. Okay? So this is your break time. This is your break time. Break time. Okay? So I'll see you all at 5:20 p.m. Yes. Hi everyone. Yes, everybody. Let me know if I'm clearly visible and audible to all of your not students, everybody in the chat box. Do let me know. So the break is over and let us resume the session. Let us see, and do let me know before this if you have any problem. Right? Before this, what we have discussed, if you have any problem, do let me know in the chat box. Ma'am, I have prepared short formulas and tricks. Very good. If you have prepared that, then do let us know in the comment section as well the tricks that you have prepared, and also you can post it on our Telegram channel as well. Right? Okay, so let's see that. Let's start with ionization enthalpy. Yes, students, let's start with ionization enthalpy. So, okay, Veena, I'll take it into consideration. Firstly, let me just complete this series, right? That we will also, I'll take it into consideration, okay? Let's see. Now let's talk about ionization enthalpies. If you see, along the period, what is happening, size is decreasing. And we know that ionization enthalpy and size is inversely proportional to each other. So that means if size is decreasing, ionization enthalpy should increase along the period. So that is a general trend that we think that ionization enthalpy should increase. So here it is, that is said, increase in ionization enthalpy along each series of transition element due to increase in nuclear charge. Nuclear charge is increasing, that will also increase, which accompanies the filling of d orbitals. Now there are also weird order that we will see here. Values of first ionization enthalpy of the series, the values show the successive enthalpies do not increase as steeply as in the case of non-transition elements. As you can see from the values over here, they are not increasing. So first ionization in enthalpy is increasing or decreasing by a very small factor. Can you see second ionization enthalpy is increasing by a large factor? 1200 to 1300 to 1400 to 1500, then to 16, 17, then suddenly to 19. Can you see the increment in the second ionization enthalpy is high? In case of third ionization enthalpy, it is even higher. Can you see? By the gap of 1 or 2000, it is increasing or decreasing. So the increment is even higher than we expect, right? So the increment is even higher than we expect here. So we'll also understand what is the reason behind that. We'll also understand the reason behind that, right? The value shows successive enthalpies do not increase as steeply in case of non-transition elements, right? The variation in ionization enthalpy along a period of non-transition is much less. In first ionization enthalpy, the variation, the difference is very less. The first ionization enthalpy in general increases, but the magnitude of increase in the second and third ionization enthalpy is much higher. Two comparisons we have done. First is first ionization enthalpy with second and third ionization enthalpy. First ionization enthalpy increment is very less. Then first, the ionization enthalpy of transition elements, they have less increment or decrement as compared to non-transition elements like S block, P block, right? Their ionization enthalpy increases to next level. Why? Because again the same thing it is there, because the difference in n-1d and 4s orbital is very less, right? The irregular trend, now we are talking about irregular trend of this through the chemical significance can be accounted by considering that removal of one electron alters the relative energy of this and this. So we'll see that why it is that we have learned when D block. Firstly, I'll just show you the trend here, right? Then we will study all of that. What is the irregular trend of ionization enthalpy? See, ionization enthalpy, IE1 trend I am writing here, right? Or should I write IE1, IE2 both? Where should I write that then? Okay, let's see. IE1, firstly I'll write. Okay, IE1 trend, guys, I am writing. Always write it like this. Succative. You know what? I'll not write it here. IE2 trend I can write here. IE1 trend you can also write over here. Right? You can also write the IE1 trend over here. Just write it like this. This you should remember as it is. Succative Karman Fico, right? Fico Ni Ku Jan. Now the enthalpies should increase, right, along the period, but in front of V coni it will decrease. The sign will be opposite. V coni it will be this, this and this. Rest of the things it will be same, that is this. That is going to be the order, right? That is going to be the order. You can also check this order here. Firstly, scandium. Scandium to titanium it will increase, then it will decrease in front of vanadium. Then again it will increase, then again it will decrease in front of cobalt. Then again it will decrease in front of nickel, then increase. Got it? So it is decreasing in front. IE1 is decreasing in front of V coni. IE1 is decreasing in front of V coni. And IE2 will decrease in front of what? Right, let's see. Let's see, IE2 will decrease in front of which of the following? Right, let's talk about that. Right, okay. Ionic radius we have discussed. Acha. Let's talk about this now. It will increase, increases there. Now here, in front of manganese, you will see the decrement. Then increase. Then in front of zinc, you will see the decrement. Right? Okay. So IE2 will decrease in front of manganese and zinc. So you can just write it like this. Just remember these two things. It will like really make your, you don't have to cram these things then. You don't have to learn full order here. V coni, in front of V coni it decreases, and then in manganese and zinc it decreases. Right? Otherwise it will go increasing. Only in these cases you will see the exceptions. Tell me. Is that clear? In front of these two cases, you will see the exception. Others will be increment. That's it, you have to remember. Right? IE1 and IE2. So you can see even, let's see in IE3 also if there is any weird thing that you can see. Increase. Here decrement is in front of iron. Then increase. Only in front of iron you have the decrement. Right? Only in front of iron you have the decrement. So you can also write this here. In IE3, only in front of iron it decreases, others it will always increase. Okay? Tell me. Right, everybody? Clear? Only in front of iron it will decrease, in front of other things it will always increase here. Clear everyone? Shall we move ahead? Now let's see what is written in the theory part. Now you'll be able to understand it more, right? The irregular trend in first transition enthalpy 3D series through little chemical significance can be accounted by considering removal. Why there is this trend is not irregular? Why it is irregular? Considering that removal of one electron alters the relative energies of 4s and 3D. So what exactly happens? That when you remove one electron already, like M positive, M2 positive, they all will have different tendency of losing the electron. A positive cation will have less tendency to lose the electron. That's why more energy is required there. That's why you will see why here it is 600, why it is 12, why it is 23. Why we have ionization enthalpy? Why it is so that IE1 is greater than IE1. If you see it from here, can you write this here that IE1 is less than IE2 is less than IE3? Why? Because the difference in the energies, if you say if there is a metal, it loses electron and become metal positive. A cation will have less tendency to lose the electron. So more energy should be given to it to lose the electron. Then if it becomes M2 positive, even more energy is required. So if less energy is needed, that means it is easily it wants to lose the electron. If more energy is required, that means it's very difficult for that atom to lose the electron. And because cation, more the positive charge, less tendency will be there to lose, because positive charge means it is becoming electron deficient, and an electron deficient species has less tendency to lose the electron. Guys, I just remembered something. Just give me a second. Okay. I'm so sorry. Yes. Okay. So that is there. Then this is all we are discussing. We have learned that when d orbitals, d block elements form ions, ns electrons are lost before n minus 1 d electron. Ns electrons are lost. As we move along the period 3D series, we can see that nuclear charge is increasing. Nuclear charge is increasing. Wait a minute. Nuclear charge is increasing here. Where we were. These 3D electrons, where we were. We can see that nuclear charge increases from scandium to zinc. More the electrons you are adding, more nuclear charge, more protons will be there, more nuclear charge will be there. But the electrons are added to the orbital of inner subshell, which does not have a good shielding effect. These 3D electrons shield 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another. 3D electrons are still better than 4s electron, how they are shielding each other. Therefore, atomic radii decreases less rapidly. Therefore, the decrement in the atomic radii is not that much, but it is decreasing. This ionization energies increase only slightly along the 3D series. That's why very less increment is there, right, along the series. The doubly or more highly charged ions have DN configuration with no 4s electron. If you talk about IE2, IE3, then from 4s, see, let's say you have electronic configuration 3D5 4s2. Let's say this is manganese. Now you have manganese positive. Manganese positive, it is 3d5 4s1. Now you have manganese 2 positive, that is 3d5 only. So now you don't have in IE3, when you want to lose the third electron, then you don't have any 4s electron. You only have 3d electron. It has high charge as well. So no 4s electron is there. A general trend of increasing values of second ionization enthalpy is expected as effective nuclear charge increases because of d electron does not shield one another. Now they are saying that why IE2 and IE3 is greater. See, protons are still there. If initially 25 protons, 25 is the atomic number, 25 protons, wait a minute, why I have written it like this. See, in manganese, you have 25 proton, 25 electron. In manganese positive, you have 25 protons, 24 electrons. In manganese 2 positive, you have 25 protons, you have 23 electrons. And here it is 4s2, 3d5, here it is 3d5, 4s1, here it is only 3d5. So in manganese 2 positive, you don't have any 4s electron as well. You have more proton, that means more charge from proton is there, and these 3d electrons don't have good shielding effect as well. So all these factors are making the electron closer to the nucleus, and hence that is the reason the energy needed to take out one more electron will be very high. Do you get it? Okay, does not shield one another electron. The influence of nuclear charge because of d orbitals differ in direction. However, the trend of steady increase in second, third ionization enthalpy breaks for manganese and Fe3 positive, right, respectively. Now we know that this all you don't need to underline that, so I have explained you over here in a simpler way. But this is an important line to underline, that Mn2 positive, zinc 2 positive, Fe3 positive, suddenly they require less IE. Now these questions they can ask you why it is so. In both cases, ions have D5 configuration. If you see here, okay, I'll just put it here. If you see here, you have manganese, that is 4s2 3d5, right? Manganese positive is 2 positive is 3d5, which is a very stable configuration. To take out 2 electrons from here will be quite easy. Why to take out 2 electrons from here is an easy task? Because it is getting converted to a stable configuration. So that is why Mn2 positive, right? If you see, that is why we know that the trend of steady increase in second and third ionization energy. So when you are forming, when you are taking, let's say IE1, when you are taking the first electron, that is easy. Second electron is super easy. I'll tell you how. This is biggest mistake that students do, which is first and which is, this IE is 1, another IE is 2. Okay. So manganese positive is 4s1 3d5 and manganese 2 positive is 4s0 3d5, which is quite stable. So this IE2 is actually not, we can't say the second ionization energy will be very like as you go from here, Karman, here it is supposed to be really high. But now what will happen? The second ionization enthalpy that you need will be less. Can you tell me why? We have seen this there. We have seen it in the exception that in case of ionization, manganese and zinc is less second I. But what is the reason behind that? The reason is that in case of Mn2 positive, you're getting into a stable electronic configuration, then why you will need a very high energy? You don't need an high energy. You are happy with low energy as well. So that is the reason here we can say low energy is required, and that is fine. Now let's talk about iron. Let's talk about iron. Iron is nothing but it is 4s2 3d6, right? Now when iron loses one electron, it is IE1. IE1 is 4s1 3d6. It loses another, that is IE2. It becomes 4s0 3d6. Still it is not in a stable configuration. Then it needs IE3. Here it is becoming 4s0 3d5, which is a very stable configuration, which is again a very stable. So IE3. So as you talk about Saktiv Karman phi. So here what you will see in the trend, it is increasing, but at iron it suddenly drops. Why at iron it suddenly drops? That I have written over here as well. At iron it will drop. At iron, why it suddenly drops? Because it is now, when I tell you that you study, then you will get into aims. Then you are like, ma'am, I'll study. If I say that you study, but you will get nothing in your life, then you will say, ma'am, why would I study? So if it is getting converted to a stable configuration, no energy is required to make it lose the electron, right? Less energy is required. So that's why here IE3 decreases in case of iron, right? That is the thing that they have talked about here, right? Okay, this is the thing that we have talked about in this particular case, right? Then in both these cases, ions have D5 configuration. The interpretation of variation in ion electronic configuration is as follows. The three terms responsible for variation of ionization enthalpy are attraction of each electron towards the nucleus. How much attraction is there? If attraction is very high, it's very difficult to lose that electron. Repulsion between electron and exchange energy. How much repulsion is? Repulsion is high, it's very easy to lose the electron. Exchange energy is responsible for stabilization of energy state. Like in case of D5, D10, exchange energy is very high. That's why it gives it the stability. That's why taking out the electron is very difficult. Approximately proportional to total number of possible pairs of parallel spins. What is exchange energy? That is total number of possible pair of parallel spins in the degenerate orbitals, total possible pairs of parallel spins. So if it is 1, 2, 3, 4, 5, it has 5 parallel spins. 6, 7, 8, 9, 10, it have again 5 plus 5 parallel spins, total 10 spins that are parallel. Okay. Several electrons occupy a set of degenerate orbital. The lowest energy state correspond to maximum possible extent of. Now what we are saying that till here though it is clear what is exchange energy. Now we are saying when several electrons occupy a set of degenerate orbital. Degenerate means having the same energy. Lowest energy state corresponds to maximum possible extent of single occupation of orbital and parallel spins. Loss of exchange energy increases the stability. That means, beta, they are simply saying that if you have, let's say, degenerate orbitals, right? You have parallel spins here, like 1, 2, 3, 4. This can exchange here, 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 here, here. This can exchange here and here. So these are the pairs that can, but they will exchange only to the lower energy. That means several electrons occupy a set of degenerate. The lowest energy state corresponds to maximum possible extent of single occupation of orbital and parallel spins, right? Maximum how many parallel spins you have, right? So that defines the exchange energy, right? How many exchanges are possible. As the now more is the exchange energy is maximum in D5, and all the orbitals should look same in exchange energy. As the stability increases, ionization energy became more difficult because stability is increasing. There is no exchange energy of D6 configuration. Manganese has this configuration and configuration of chromium is this. Therefore, ionization enthalpy of manganese positive is lower than chromium. Now, this is another thing. You don't have to even see this. See, just see this thing here. They are saying just point out this thing here. Ionization enthalpy of manganese is lower than chromium. Can you tell me why? A simple thing is chromium is 4s1 3d5. Manganese is 4s2 3d5. You take out one electron from chromium, this will become 4s0 3d5. You take out one electron from manganese, it will become 4s1 3d5. So if you take out one more electron here, that is 3d5, that is quite easy. When you take out one more electron from here, this becomes 3d5. This is easy because this is getting converted into a stable electronic configuration, right? But when you take out one electron from here, it's not possible. That is why chromium positive has very high ionization enthalpy and ionization enthalpy of manganese is less. So whenever these kind of statements are given to you, you don't have to learn this. You just have to write down the, wait a minute. Okay. Yes. So in the same way, now they are again saying that iron has D6 configuration and Mn2 positive has D5. So Mn2 pies to take out one electron from Mn2 positive, it is very difficult, right? Okay. But to take out electron from Fe2 positive, it's quite easy, right? Okay. Right? So to take out electron from D6 configuration and make it D5 configuration, it is easy. That is why ionization enthalpy is very low. But to take out electron, this is Fe2 positive, but to take out electron from Mn2 positive, that is D5, and make it D4, it's tough. It's very difficult. That's why IE will be very high. That's why we are saying Fe2 positive will have lower IE than Mn2 positive. Why? Because unstable to stable state, less IE is needed. Stable to unstable state, more IE is needed, right? Okay. Then guys, we have, and after when there is, see, iron to iron positive, that is first ionization. Iron to iron 2 positive, that is second. So iron 2 positive to iron 3 positive, that is third ionization energy. That means we are talking about third ionization energies here, right? Okay, we'll just simply say that. Right, everybody? Tell me, is that clear? Is that clear, students? Now let's see. The lowest common oxidation state of these metals are +2. Now let's talk about the oxidation states, right? I think ionization enthalpy topic is done. That you will answer only on the basis of simply electronic configuration. You can answer based on that, right? You can simply answer it based on the electronic configuration regarding that. Now we are going to start with, yes. Okay. Now we are going to start with the oxidation states. Let's see that. Yes, everybody. Let's start with the oxidation states. Let's start with the oxidation states. So we are saying that variable oxidation states are there. Lowest common oxidation state of these metal is +2, nickel +2, then you have manganese +2, iron +2, lowest oxidation +1 you will rarely see, right? The form to form M2 positive from the gaseous atom, the sum of first and second ionization enthalpy is required in addition to enthalpy of atomization. So, firstly, you need to break the atoms. Firstly, they are like this stage. This is how the atoms are. Firstly, you need to break these atoms. Then you have a gaseous atom. Then you will take one electron. Then you will take two electron, and that's how you will have M2 positive, right? So, three things are required here for oxidation state. We'll focus on three things. First is IE1, then there is IE2, then there is enthalpy of atomization. First, second ionization enthalpy, then there is enthalpy of atomization, right? Okay. Dominant term is the second ionization enthalpy, which shows unusually high value of chromium and copper. Now, dominant term we are saying is chromium and copper, because see, chromium has 3d5, right? Copper has 3d10. See, chromium positive has 3d5, copper positive has 3d10. That is why to take out one more electron from here, it's very difficult. So, ionization, second ionization enthalpy of chromium and copper is very high. Where M positive ions have these electronic configurations, the values of zinc is corresponding low. Why zinc is corresponding low? Because zinc, if you see, zinc is 4s2 3d2 3d10. To become Zn2 positive, it is getting into a stable electronic configuration of 3d10. Then why it will not want to get converted to 3d10? It's giving a stable configuration, so it is easy. So for zinc, value is low, right? Value is low. As a removal is it is converted to stable D10 configuration. The trend in the third ionization enthalpy is not complicated by 4s orbital factor and shows greater difficulty of removing an electron to form D5 and D10 configuration. Now we are saying that if you further talk about the Mn2 positive that has D5 configuration, Zn2 positive that has D. After this, you want to take out 1 electrons from Mn2 positive and Zn2 positive. It's not possible. That's why Mn3 positive is not stable. Zn3 positive, so you will never see only, right? In general, the third ionization enthalpy are quite high. Also, high values of for third ionization enthalpy of copper, nickel, zinc indicate copper, nickel and zinc have very high values. Why it is difficult to obtain oxidation state greater than 2 for these elements. So that's why most stable state is +2, where +2 you will see for almost all the elements exist in +2. But there are only few elements that exist in +3, +4, +5, +6, +7, right? Although IE gives more guidance concerning relative stability of oxidation, the problem is very complex and not amenable to have any generalization. So we will not study it here. So that's the good thing that we are not studying it here, right? Till now we only talked about that how this plays a very important role, how this ionization enthalpy plays a very important role here. Next part is oxidation. So oxidation, if you see this chart here, can you see some things that are written in bold? What are these things? There are several oxidation states. Now we will try to study more from tables rather than from these this theory part. Let's see this, right? Let's see this. Let's understand this part here. So we can see over here that oxidation state of first row metals, if you see scandium is +3, +2, +2, +2 is very very stable state. Now with the bold, can you see some of these are in bold, right? Some of these are not. The one that are in bold are actually stable oxidation state of that element. Like titanium is stable in +4, vanadium is stable in +5, chromium is stable in +6 and +3, right? Okay. Mostly you will see they exist in these things. Manganese is stable in +2 and +7, right? Then you have iron is stable in +2 and +3, and you will see mostly iron in +2 and +3 only. You will never see anything else, right? Cobalt is stable in +2 and +3. Nickel is stable in +2, right? And copper is stable in +2. That's a weird thing, and we'll also talk about that. Zinc is stable in +2. So these are all the values that they have marked in bold in your NCERT. Which state is more stable? Now, can you see a pattern here? That is also written in your NCERT lines. That from scandium to manganese, higher oxidation states are more stable, right? Higher oxidation. So scandium only has one state, so what's the point of stability? Zinc only has one state, so what's the point of stability? But you can say from titanium to manganese, higher oxidation states are more stable. But in case of after manganese, iron, higher state is not stable here, right? So you can say up to manganese, higher oxidation states are more stable. But after manganese, higher oxidation states are not stable here. Can we say that, everybody? This is also written in your NCERT, okay? Let's see that. Greater variety of oxidation state is there, right? Let's see. We have also seen the varieties here. Let's see what we talk about now. These points is where students usually starts getting stuck, right? Let's see. Elements which give greatest number of oxidation states occur in or near the middle of the series. So we can say manganese has maximum number of oxidation states. These points that I am writing now, these are very important. They can ask you directly this. Manganese, for example, exhibit +2 to +7, lesser the number of oxidation state at the extreme ends from either side, from either too few electrons to lose or share. Wait a minute. The lesser number of oxidation state at the extreme end stems from either too few electrons to lose or share for scandium, titanium, or too many d electrons and fewer orbital available in which to share electrons with others. So basically they are saying that in case of scandium, titanium, it is 4s2 3d1, 4s2 3d2, 4s2 3d3. So why they have less configuration, especially in case of scandium and titanium? Because the d plus s orbital electrons is less. But over here, why they have less? Because this is d10 and s2, right? So here they are mostly unpaired electrons are less, right? Here unpaired electrons are less. That means the oxidation state depends upon the unpaired electron. In manganese, you have maximum number of unpaired electron. That's why oxidation state is maximum. So we don't only need electrons in d orbitals, we need unpaired electrons in the d orbitals, right? Okay. Okay. So too many electrons for higher this. Thus, early in the series of scandium is virtually known, and titanium 4 is more stable than titanium 3, titanium 2. So, all these things that I'll be writing here is actually written here, right? Okay, so I'll be pointing just important parts here. First is lesser number of oxidation state at the extreme ends are there, right? Greatest number of oxidation state occurs near the middle of the series, that is manganese, right, which exhibit +7 +2 to +7. Then we are saying titanium 4 is more stable than titanium 3 and titanium 2, right? Because titanium 4 positive has, titanium is nothing but 4s2 3d2. Titanium 4 positive will have 3d0. That's why it is more stable, right? At the other end, only oxidation state of zinc is +2. No d electrons are involved in the case of zinc. The maximum oxidation state of reasonable stability corresponds to the value of sum of S and D. Now, what we are saying, maximum oxidation state of reasonable stability corresponds to the value of S plus D electrons up to men. This is a very important line, very, very important line. I'll just mark it with this pen here. That maximum number of oxidation state that has the stability, that depends upon S plus D up to manganese. That's why up to manganese you have S plus D is 4, S plus D is 5, S plus D is 6, S plus D is 7, right? That's why up to manganese maximum oxidation state corresponds to, you'll just write it over here as well, up to manganese. Simple language I am writing, maximum oxidation state is Ns plus Nd electrons. Okay, maximum oxidation state will be Ns plus Nd. This is a very important line. Like you have titanium 4, vanadium 5, chromium 6, manganese 7. These are having maximum N plus D electron here, right? Followed by rather abrupt decrease in stability of higher oxidation states. After that, decrease. So that typical species to follow are iron 2 and 3, iron 4, 6 does not exist, cobalt 2 and 3, nickel 2, copper 1 and 2, zinc 1. So what you are saying that after this, after manganese, iron is 4s2, 3d6. So it should be +8. This is 4s2, 3d7. It should be 7, 8, 9. It is 4s2, 3d 8. So it should be 10. But we are not even talking about those oxidation states. So that is why after that lower oxidation states are more stable. This is a very important thing that we have just discussed here, right? Okay. Up to manganese, higher oxidation states are more stable. After manganese, it changes. Next is the variability of oxidation state, a character of, if you talk about the variability. Now we are seeing the variability of oxidation state, right? Characteristics of transition elements and arises out of incomplete filling of d orbitals in such a way that their oxidation state differ from each other by unity. Now what we are saying here, wait a minute. I think I should just teach you with this one only. The variability of oxidation state. That means we are saying the oxidation states are variable. A characteristics of transition elements arises out of incomplete filling of d orbital. We are saying incomplete filling of d orbital is there in such a way that their oxidation state differ from each other by only unity. Now this is a very important point, that in case of here, the oxidation states are only differing by unity. 2, 3, 4, 5, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7, right? Their oxidation states are only variating with the change of 1, right? The variability of oxidation state is only unity here. right? For example, vanadium 2, 3, 4, 5. This is contrast with variability of oxidation state of non-transition elements. If you talk about non-transition elements, let's say you talk about oxygen, it is not, if you talk about when you study P block, oxygen is NS2 NP6. Either it can be plus, sorry, not NS2 NP6, either it can be -2, +2, +8, these can be +6, sorry, these can be the oxidation states. They are not differing by unity here. Let's say nitrogen here, right? Sorry, oxygen, I wrote it wrong. Oxygen will be NS2NP4, right? So it has +4, it has +6, it has -2. Are they variating by a unity factor? No, right? That will, if those who have not studied P block, they won't be able to understand this thing, that why P block I have written it like that. That will study in P block. Just remember variability of oxidation state, right? It is there. It is different from non-transition elements. In non-transition element, the difference is not of unity. Here you can say oxidation states differ from each other by unity. Oxidation states, they differ from each other by a factor of unity only, right? Okay, understood? This particular line was very, very important, so I am just highlighting this part so that when you get your notes of this particular thing, then you also remember that what ma'am told you here. Okay, here also I'll just highlight whatever I have discussed till now, right? Tell me, but is there any problem till here what we have understood, right? Tell me everyone, is there any problem till here, right? Okay, let's see. Let's study the next part here. An interesting feature, now what we are saying, that a very interesting feature of the variability of oxidation state of D block element is noticed among the groups, group number 4 through 10. 4 through 10, what we see, interesting feature is that although the P block, the lower oxidation states are favored by heavier members, the opposite is true in case of D block element. Here you will see group number 6 is preferring, now this is a very important point, again just highlight this, this is like very, very important point, like a very important paragraph this is. Okay, from there, like a lot of questions they ask you from here. So they are saying down the group, in P block what happens, down the group, lower oxidation states are preferred, right? Let's say you have nitrogen, it shows +3 and +5 oxidation states, so +3 will be preferred lower down the group. But in case, here if I talk about thing that they have given, chromium, molybdenum and tungsten, right? They are there. So you have higher oxidation status +6, +6 and +6. In this case, higher oxidation state is preferred. This is a very important point, that you have chromium, molybdenum and tungsten, and +6, that means higher oxidation state is preferred. Higher oxidation state. Preferred, I am writing in a simpler way, preferred down the group. In heavier element you can say, or down the group. This is a very, very important point. You must highlight this. You must highlight this over here. It's a very, very important point. I'll just highlight everything that is important here. That is, in P block, lower oxidation states are favored by heavier metal, that is down the group P block elements, that is preferred. But in this case, molybdenum 4 and molybdenum 6 and this are found to be more stable than chromium this. Why molybdenum and this are more stable as compared to chromium? Because heavier high oxidation state is preferred down the group. Chromium 6 is in the form of dichromate in acidic medium, is strong oxidizing agent, whereas this and this. See, chromium 6 positive is exist in like dichromate ions, it exists in chromate ion, it is existing, but in case of molybdenum, MO3 and tungsten O3, where it is existing in +6 oxidation state, it is stable, right? So it's a very, very important point, right? This is a very, very important point, right? That I have, in a simpler way, I have written it over here. This is a simple language that I have used here. Okay, got it? Tell me, got it, everybody? Now, lower oxidation states are found when complex compounds has, they are saying when the lower oxidation states are found, we are saying lower oxidation states are also found when the complex compound has ligand capable of pi acceptor in addition to sigma bonding. Can you tell me? This means they are talking about back bonding. Karen, lower oxidation states are also found stable here, but that is in case when they are showing synergic bonding, they are showing back bonding. In those cases, lower oxidation states are found to be more stable. Tell. In those cases, lower oxidation states are found to be more stable. Is that clear? Done, everybody? Okay. So nickel, cobalt 4, iron, CO5, these are very stable oxidation states, right? Okay, everyone, is that clear? Okay, right? Acha. Tell me, rest of the things let's do in the next class. What say? Let's do it in the next class. Hai, let's do it in the next class. What say, everybody? Or do you want to complete like electrode potential as well, ma'am? After that, then like electrode potential is a big topic, right? Then this much we will complete. After that, we'll stop. Rest of, these things, this one, to study all these things, now you really, really need to have like full fresh mind. This is so important. These things are so important. I can't even tell you that how many questions they ask from after this. Now the thing that we are going to start is going to get more complicated because DNF block NCERT is little difficult to understand, right? Tell me, do you want to study it in the next class? Okay, ठीक है. Chalo, before going, let's understand this thing, or let's understand everything in the next class. Let's see. Name the transition element which does not exhibit variable oxidation state. Wait a minute. Okay, then let's do this in the next class, right? We'll start. I think it will take me 3 parts to cover this, right? In next week I'll cover. Let's see. Let's make a session on Sunday. I'm thinking Sunday or tomorrow I will make the session. I'll think about it when it is okay. I think Sunday will be better, right? Then, but still we'll think about it, right? Okay. Then next class we are going to do rest of the things. Okay, everybody. So now I'll see you all in the next class where we are going to do rest of the things, right? And the PDF of what we have discussed till now will be provided to you, right? PDF of what we have discussed till now, guys, will be provided to you, right? And it will be in the description box. Okay? And do let me know, how was the session? You enjoyed the session, everyone? Enjoyed the session, everyone? Let me know. Okay. You enjoyed the session or not? Right? You want more of it? Then share this particular channel and my session to other students as well, and write it down in the comment section, right? At least 20 plus comments I want to see in the comment section. Okay, then only I'll continue the series, otherwise I'll not continue, right? Okay, so write down your comments in the comment section. Till then, bye bye everyone. See you in the next class. Bye bye, and I'll inform you on the Telegram channel when is the next class. By tomorrow morning and by today night, I'll inform you that. Right? Okay then, guys. Bye bye. See you all in the next class in the part 2 of NCERT